brute force, sorry, top down to bottom up to actually bottom up optimize. Let's quickly have a look what the problem says. Again, proper intuition will go on for this problem, but in the beginning I just tell the only reason is so that people just stick on that what's gonna be come, like what's gonna come in the later video. So basically it says that we are given an integer array ARR, and partition, we have to partition the array into continuous sub arrays of length at most k, which means if this is an array, you have to partition that array, but the length should be at max or at most k. And after the partition, each sub array whatsoever you have got has their value. Again, the partition, let's say I have this as the first partition. So like for each sub array, let's say this is one partition, this is other partition, this is other partition. Let's imagine, again, I have not considered this k for right now, but yeah, by default it is automatically considered. But still, let's say if this is partitioned, then for each sub array, which means for this specific sub array, their values changed to become the maximum value of that sub array. So their values, which means for this specific sub array, their values will become the maximum value of the sub array, which means 15, 15, 15. The maximum value for the sub array is 15. So each value will become maximum value of that sub array. Now we have to return the largest sum of the given array partitioning. So as you can see, I just partitioned this array. So I have to give the possible largest sum. And again, when I say this partition, okay, for this specific sub array, the maximum value is 9, so all the values will be converted to 9. For this, the maximum value is 10, so all the values will be converted to 10. Okay, now just make sure that you might think, okay, Aryan, the constraint said every value is 1e9, I have 500 values, so I might go out of bounds. But yeah, that is true. But for the interview, you should verify that okay, interviewer sir, is it possible because of the constraints your summation can go out of bound for a specific sub array? Then you might just say, should I take a long or not? But the problem says that the test cases are generated so that the answer is in 32-bit integer, which means these partitions array sum and also the total array sum, final array sum, all answer is in 32-bit integer, which is the maximum which you can have, and you have to return the largest or the maximum possible sum. So by default, let's look at the one example. Although we have got the proper idea that okay, what the partition means, what the partition size can be, all that stuff, but still have a quick example that we have k as 3, which means saying that my maximum partition size can be a 3. So I can see that okay, I can have a 2 size, 3 size, 2 size of 2. So for sure it is all size. Okay, 2 is less than 3, 3 is less than 3, 2 is less than 3. So my size can be less than equal to my partition size, which is k. And for that, okay, if I take this as the first partition or the first sub array, maximum element in this is 15. So I'll transform all the elements to 15. Okay, 9, all the elements to 9 because maximum element is 9. Here maximum element is 10. So all the elements to 10. And that's how, if I just sum this up, it's partition. This specific partition will have the specific sum. And again, the other variation can be if I do a partition here, and partition here. So you can see size 3, size 1, size 3. So I did not go beyond the size of 3. So that's cool. The partition is actually great. So I'll simply say maximum element 15, 15, 15, 15, maximum element 9, 9, maximum element 10, 10 to 10. So the sum for sure, you can easily visible that okay, I have a 10, 10 here. This 10, if you just compare these values, so for sure this got replaced to 10, which means one more 10 came in, and here one more 15 came in. So for sure this value is much larger than this value. So this is the maximum sum, and as you can see, the answer also says that this partition, this specific sub array partition will give you the maximum sum possible, and that is my answer also. But one of the cases which is a non-valid case, it can be that okay, what if you, because we wanted the maximum sum, so you just did greedily, okay, the maximum partition here, and all that stuff. So one thing is for sure, you might extend the k size. As you can see, I have did 5 elements in one partition, which is not possible. So I can only have 3 elements in one partition. So this kind of variations, which means okay, you are going beyond your k limit, that is not allowed at all. Now for sure, this simple basic comes in picture. Okay, as you can see also, I tried the first sub array of size 2, then size 3, and I can try for all the possibilities. No, so why not try for all the possibilities? But Aryan, if you will go and try for all the possibilities, which means if you just remember stars and bars, Again, if you're not known, just write on YouTube math by Aryan Mittal. You will get a playlist, which is the math playlist. In that we have discussed about stars and bars, which is nothing but saying if I have 5 balls and I want to divide that into 3 partitions, then how many number of ways I have. Again, this will give me all number of ways, but I want only the one in which the partition sizes are restricted or bounded by some specific k dash, right? So in this, when after that you will generate all the possible ways, then you have to go on and check if the partition, individual partition, matches the size or not. So the complexity, if you go on by recursion, then the complexity will be nothing but factorial, or you can just roughly say to the interviewer, it can be exponential. Exponential is nothing but saying it will be very high, but actually it will be a factorial time complexity, which is actually again very high. Even 10 factorial is very high number. So still factorial complexity, which means going on and again, and that's just one part, which means n-1 ck-1. That's just one part. Then you will have to iterate on the entire portion, which is again an n, and then you have to go and find, okay, what is the partition sum. So you can just do that in this time to actually get the answer, but still that is way too much high and you cannot solve it. So coming on back, that how we can easily solve it. So for sure we got to know that recursion might not work, but maybe we can something figure out in recursion. Yeah, we will do the exact same thing. Whenever something like that, okay, you have to try for all the possibilities, but you can see the brute force or the very standard approach of recursion will have a very high complexity. Then you know that, okay, you will try for maybe to think out a pattern that, okay, it's a DP. And the same way happens, and although by now you must have figured out by reading the problem itself in your mind that, okay, it should be a DP, and I'll tell you how you would have figured out earlier. But right now let's see that how it will actually happen. So earlier in a standard, you are at your first index. Now you want to try for all the sizes. You want to try for all the sizes, and you know that your maximum size is k. So you will try your first partition to have a size of 1, next partition to have a size of 2, next to have a size of 3, next to have a size of 4. 4 cannot come because 3 is the maximum limit. So you will try for size of 1, 2 and 3 for the first partition. Okay, now you will ask your recursion, bro, okay, I will give you the sum of this partition. I'll give you the sum. Again, the sum will be get the maximum value in that specific partition. For this is 1, for this is 15, for this is 15, and the maximum value is there. Now replace all the values, which means I had 1, 15 and 7. Replace all these with the 15. So I can simply say this specific partition will contribute in my answer as 15, which is the maximum value, into the number of elements, which is 3. And the same way it will contribute as 15 into 2. 15 maximum value into number of elements, because I know that maximum element will be repeated number of times. Here it will be 1 into 1. Now I'll simply go and ask my recursion, bros, hey, hold on, I did my work. I did and found the answer. Now it is your responsibility. Go and find the answer for the remaining portion. So again, you will see, okay, your I was at the very beginning. I was at the very beginning. Then your J tried for all the possibilities. J was here, then J was here, and then J was here. So you can easily see that your J went on up till less than I plus K. Because if your I was at the 0 index, your K is 3. So you went up till the index 2. Now I plus K is 3. So you went less than I plus K. Now Aryan, what if my I would have been here? So I plus K would have been here. So yeah, you cannot for sure go beyond the array. So also put a limit. Okay, you should also be less than n. Thus my J for every I, my J, which means for every I, which means, okay, from here itself I'm starting to do my partition. And I will try for length 1, length 2, length 3, length 4, length up till length K. So I'll just say try your J less than n, because for sure you cannot go beyond the n, and it will be less than I plus K. This is your J you will be trying on, and you can see that, okay, here also I tried my J, but it will not be tried because J is more than equal to your I plus n. Your J will be tried up till here at this point. Now you have known, okay, this you will calculate, and the remaining, which means starting off with J plus 1 with the same concept, bro, go and find the maximum sum. So he will just go and say, starting from J plus 1, go and find the answer. So this will be handled by recursion itself. Now Aryan, okay, that sounds great, but where's the repeat is a problem? Because DP is applied when you have a repeat is a problem. Show me that. For sure I will not build the entire tree, but in this specific example itself, if, okay, first partition is done, okay, it is having one element which is 1. Let's say for this, the first partition is done, having element 1, 15 and 7. For the next partition, let's say for this, for the next partition, let's say it took 3 elements. Again, it will try for all the possibilities also. It will try for 1, for 2, for 3. But for now, let's say that, okay, I build on the 3 possibility, which means the next partition took 3 elements. So you can see it took 3 elements. For here also, it will try for all the possibilities, 1, 2, 3 and all that stuff. But let's say for now, it imagined that, okay, it took 1 as the one, next partition size is 1. Okay, next partition size is 1. Then your recursion will say, okay, bro, now for the next partition, which means for the third partition, start from 2. Start from 2. And thus you can see, this is the repeating subproblem. This is the repeating subproblem. That is how, because you can easily see, okay, 1, 15, 7, 9. 1 was one partition, 15, 7, 9 was other. Here 1, 15, 7 was 1 and 9 was other. So that is how you can see it is a repeating subproblem. Now you know that, okay, rather when you start and go and find the maximum which j plus 1 can give, you will just simply memorize that. And thus I know I'll use my TP. Now a quick recap of what we will actually return. As you remember that this, I want to give the maximum possible sum, largest sum. Remember, largest sum I want to give. So I will simply say, okay, this sum I can easily grab while iterating on my j itself, because one way is I get to know the partition and then I again iterate on the entire I to j to get the largest value, and then took, okay, the maximum value is 15, the number of times it will repeat it is j minus I plus 1. So the sum contribution of that specific partition will be maximum value into the size of this specific the partition, which is 15 to 30. So one way is that you again and again find the maximum value again and again for every partition. Like for this first partition, as you keep on expanding, okay, j was here, then j was here, then j was here, and my j was here. So when I and j was here, then you find the maximum value while iterating on the I to j. And then my I and j was here, you again went on and again iterated the entire I to j. That's one way. But the other better way is that, okay, your I is here, so I to j maximum value is 1. Then when your j shifted, it will shift just next value. So compare with the previous maximum value to the new maximum value, which is 15 came in. So yeah, so right now your maximum value has become 15. So you are just not iterating to find the maximum value again and again. That's the same concept which also apply. Okay, you have to find the maximum in a sub array. So yeah, let's say now the j shifts again. So now you have encountered 7. So okay, maximum previous value is 15, new value is 7. So for sure, the maximum value now is still a 15. And that's how you can keep track of the maximum value. Size will be monitored by I and j. And thus I can simply get my sum of that specific partition and simply go and ask the recursion, bro, please solve it starting from j plus 1, j plus 1, j plus 1. And the recursion will give you the maximum possible sum. Again, you are getting the possible sums. So what you will return to your parent, you will just say, I want the maximum of all the possible variations which I can have, which means for the first partition, I can have size of 1, 2, 3, 4, whosoever is giving me maximum size, just get me that specific value. And sum you can easily calculate, as I showed you that I to j, you can simply calculate the sum by keeping a track of maximum value and thus times and then the sum. So your answer, which means your answer for dp of I, which means your answer for dp of I will actually become maximum of your dp of I. What's up? Because you want to maximize your sum, and dp of I is the sum starting from the ith index. And then you will firstly go and ask, okay, bro, I just took a partition from I to j. So my maximum value which I have got in that specific partition I to j, and for sure this is the maximum value, the size of that partition is j minus I plus 1. This is the contribution of that partition. But simply I'll go and also ask, bro, I to j, solve for j plus 1, solve for j plus 1. And that will be entire my dp recursion state. Let's quickly have a look at the code. It's exactly same, exactly simple. I made my nk as a global variable and my dp also global, so that I don't have to pass in again and again in my function. So you will see that I initialized my n, I initialized my k, I initialized my dp, again size n, value minus 1, because I know only indexes are being monitored here, only indexes. But Aryan, you might think, okay Aryan, why not I have stored in k, my k will also reduce. like that is obvious, no, that okay, my k is also reducing here. You will see my k is only used to know, okay, the partition size. That's it. I'm not saying my k says number of partitions left. That is the difference. If I would have said, okay, number of partitions, again, if I would have said number of partitions in the entire array can be 3, no matter what the size is, then I could have used k in my DP state. But I'm here saying this k contribution is the size of any partition. The size of any partition, it can never exceed k. That is the reason I will not use my I'll not use my k in my DP state, because I will try for all the possible sizes. I'll try for 0, 1, 2, 3. Sorry, I'll try for 1, 2, and 3 sizes possible. That's the reason my k, I am trying for all the possibilities. But for the people who are confused on when we will use k, k would have been used if I would have said I will have only 3 partitions in this array. I will have whatever the size is. I'm not worried about it. But what if I had only 3 partitions in the array, which means I'll just take first partition like this, like this. So why k would have been required? Because if I am at this point, I should be knowing that, okay, how many remaining number of partitions I have to make in the future. That is the reason when you want something at a state, which means at this index, if in my mind I want to know how many number of partitions I have to make, then only I will require my k. But here in this case, k just says the size. So no matter what the size is, I will try for all the possible sizes. I'll try for a size of 1, 2, 3 up till k. I try for all the possible size, no matter wherever my index is. I'm not concerned about the number of partitions. I'm concerned about the size of each partition. Cool. And that's how you can simply solve this answer. So now you know why your k will not come in your DP state, only your index will come, because you don't need the partition, because you will try for all the possible partition sizes. So for sure, I'll initialize my DP with n, and I'll simply solve. Go bro, I'll give you the starting index, which is 0. Let's name it as id, although you can name it as I also, but id was actually much more bigger name than I, so I gave it as id. But then for sure, a simple base case which comes in picture, that okay, if your id exceeds n, simply return a 0. For sure, if your id is itself exceeding n, return a 0. Normal recursive memoization case, that okay, dp of I minus, like if your dp of I is not equal to -1, simply return your dp of I. Now you have to find the maximum value in that I to j. So you'll try for all the possible j's up till, okay, as I showed you, I plus k and n, whosoever is less. Up till that point, you will try on and keep on getting the maximum value. And also, okay, this is the first partition which I am getting. This is the partition which I am getting. This is the maximum value, and I to j is the size. So I to j is the size, which means id to j is the size. So size will be j minus id plus 1. Maximum value will be the sum. If I just get the maximum value and just place all the values to equal to the maximum value, then this will be my entire sum of that specific partition. And go and ask Recursion, bro, solve for j plus 1. I'm not concerned about that, and store that in your dp of I. And that's how you can simply solve it. Again, the complexity will be nothing but, okay, O of n, because your dp state is going on to all the indexes, and for every index I'll try for all the possibilities of k. Okay, k has size of 1, 2, 3 up till k. So you will see time complexity is O of n into k, and space, you can see it is nothing but O of n itself. Now again, let's say if I ask you, can you please optimize it? But before optimizing, you know that you have to convert that to a bottom up. So I have this code, I will just simply directly convert to it to a bottom up. Now you see in a top down, which means top down, you are going down, which means you are going deep. In top down, you started off with an index of 0, but then ultimately in the recursion, you will keep on going up till the last index, which means the n-1 index, and then you will come back from there. So I represented the same thing as I will start off from the last index, which means n-1, and then I'll come back to the 0 index. Now when I'm starting off with any index, I know that I will keep track of the maximum value. So I keep track of the maximum value, and then as you saw that I will try from j as id to up till the id plus k or less than, or n, whosoever is less. I'll just do the exact same thing, and then update the maximum value, as you can see, update the maximum value, and then get the answer, the maximum value. Here you can see that you can also put the answer here and answer here, and then you put your DP of ID as answer. This also will work entirely, but yeah, you can also here also you can put your answer by address assigned to DP and then solve it, but both are same. Again, I could have put answer here and that would actually simply work, but I did not put it because the next thing I'm going to tell you, it will actually make you sure, okay, why how is the difference between putting an answer here and then assigning versus putting a DP ID itself. Because you can see DP ID will actually try to maximize its value. Thus I can simply put my DP ID, and thus you can see rest of the thing is exactly same. I initialize my DP of with size of n plus 1. Aryan, why n plus 1? Because as you can see, I am trying to access DP of j plus 1. Although you can put a if condition, if your j plus 1 is equal to n, simply have a 0, or else simply put a n plus 1 as the size. It will handle automatically because the value is 0 by default, and ultimately return DP of 0, and the same thing I was returning here itself. Thus I converted the exact same code to bottom approach. Time and space again remains same. Now if I ask you to optimize it, although in this question technically you cannot optimize it because your k and n both are same. But I am saying that rather than space of n, I will tell you the space of O of k. But don't go and say, okay, k and n are same, but n is very less here. In the real example case, in the interview, n will be large, k will be small. He will give you for sure. That's how the things in the programming works, that for sure n is large, k is small. The same you have seen in the priority queue and heap stuff also. So in these cases, what you will do is you will figure out, okay, what is happening in your code. You will see that for every I, I'm going and checking for just last or basically next k values, right? Next k DP values. So I know that, okay, in my DP, I need only the next k DP values. So I need my DP as a size of k. Rather than having my DP size of n, I only need my DP size of k, and that would work because I need the next k DP values. That's it. So what I could have done is, I know, okay, I can just modify that n to k. Then for sure I need to get all the values. I need to get all the DP values inside this k length. So I know this ID can be anything. So I'll do a ID mod k to bring this ID in the length of k, ID mod k, and this entire thing j plus 1 mod k. Now with this, your things will come and it should work ideally, you might think, but modulo operation of something can give a same value, which means 8 mod 2 and 6 mod 2 both are 0. So if you will assign your 6 mod 2, which means 0 is equals to, let's say, your 6 mod 2, which means your let's say your ID is 6 and your j plus 1 is, let's say, some other value, or I should say that, yeah, j plus 1 is this value 8. Now if your j plus 1 is 8 and your ID is 6, now if you will just go and say DP of 0 is nothing but maximum of DP of 0 comma this any value whatsoever is there plus your DP of 0. So you are trying to maximize your DP of 0 and you are assigning that also. Now in future, let's say a DP of 10 comes in, so you have already maximized your DP of 10 mod 2 is again a 0, so it has already been replaced, and you will just simply, because you are maximizing at the same moment, right? You are assigning and maximizing at the same moment, so your DP of 0 is being maximized parallelly while executing this condition itself. So your DP of 0 is being maximized. So when your DP of 10 mod 2 would have come in picture, it would have been automatically maximized, which is the issue in here, because I want to maximize it in the next step, because else it will happen that, okay, I have done a DP of 0, maximum value which I have got from the previous step, I'm adding it with the existing value of some other value. So again, that can be a bit confusing. Just go and use a pen and paper and build example. Again, the same example you can take, and then you can easily figure it out. So again, pen and paper is very much required for this. Now what we have seen is that if, again, I can just simply use this. I can simply use the ID mod k because I want to bring everything in the size of k. Or you can also use a sliding window thing for the k. But yeah, it is new approach which you can bring everything in the size of k. For that, I realized that I should actually make sure I put that in my answer so that I am not maximizing my id mod k. This id mod k, it can be any value x, and this j plus 1 id mod k can also be x. So while at this step I am not maximizing my dp of x, I'm not maximizing my dp of x, because if I maximize my dp of x, then what will happen is, okay, this is maximized parallelly, and then adding something more, we actually maximize it much more than required. So don't touch. While you will simply maximize your answer, and then maximizing your answer will not impact your dp of x because you are not impacting your dp of x now. But when you have tried for all the possibilities, then ultimately maximize, thus ultimately assign your dp of x with the value of answer, and that's how you can simply solve it. Again, this is a tricky thing. There's no one explains this. I don't know why, but this is a new trick in which actually you can reduce the space. Technically you cannot in this question, but it is now using a space of O of k rather than O of n. Right now O of n and k both are same, but still n can be large and k can be small, and that's how you can actually use it to optimize the space. Cool, thank you for watching. See you, goodbye, take care, bye bye.